quick revision. We start with wave and particle model. Particle model that will fulfill those Newtonian mechanics like momentum, where they have mass, the main thing is they have mass, so they can fulfill momentums, collisions. Okay, so wave model, basically they can fulfill characteristic like diffractions, interference. Photoelectric effect is where a UV light shine on the metal, and then after that the electron get the energy and come out from the metal. That is photoelectric effect. So the electron that come out is called photoelectrons. So the movement of photoelectrons causes photoelectric current. Okay, so we have two situations as you can see here: positively charged electroscope or negatively charged electroscope. So if you are using positively charged electroscope, so what happens is UV light shine on it, photoelectrons come out, and after that is attracted back because this is positively charged. It attracts the electrons, and then the gold leaf will remain like that. But for this case, if the electroscope is negatively charged, so once the photoelectrons go away from the metal, then they will just go forever, so it won't come back. Okay, so that's the difference, and in that case the negative charge decreases and this gold leaf will come back here. The repulsion is not that great already, so it will come back. Then we have law of photoelectric emissions. So we have the first law here. First law is about the relation between the intensity and the number of photoelectrons. So that means if the UV light has big intensity, then the number of photoelectrons will be greater. Second law is about the frequency and the kinetic energy. So where if the frequency of the UV light is greater, then the kinetic energy of the photoelectrons will be greater. Then the third law is about the minimum frequency required to make photoelectrons come out from the metal. So there is a minimum frequency which is called threshold frequency. So threshold frequency is the minimum frequency to make the electrons, the photoelectron, come out from the metal. So these are what we learned before. And then we can see here, okay, here we have formula now. So that time we didn't go through any formula, so now we have to go through the formula now. So particulate nature of electromagnetic radiations. Particulate nature. So of course this particulate nature we discussed already. Let's take a quick revision first before we look at the calculation, which is 12.6. You can see here wave particle duality. So the electromagnetic radiation, right, the UV light that shine on the metal, it has wave behavior because diffraction happens, interference happens to the UV light. So of course that is something that we should know already from AS physics. So UV light is electromagnetic radiation, so it is wave. Wave goes through diffraction and interference. But it has particle behavior also. So it's like collision happens, the UV light shine on the metal, the zinc metal, so it's like it collide with the zinc metal, then it collide with the electron over there and make the electron come out. So it is like having the collisions effect, which is the particle behavior. We call it photoelectric effect. So that's why the electromagnetic radiation have wave behavior, have particle behavior. It has both behavior, and we call we use the terms photon to represent the particles in the UV light. So we call it photons. So if you are wondering what is photon, right? Photon is basically energy. It's a packet of energy. A photon. Okay? Photon is a packet of energy. So imagine you put those energy in a balloon, and that balloon with energy strike the metal, and then the metal, the electrons in the metal come out from the metal. That is because of the photons. So photon is a packet of energy. So sorry. Yes, this word is in IG. So that's why you feel like packets of energy you heard before, right? Yeah. Okay. So now let's see here. Um, Energy of an electromagnetic wave doesn't flow continuously, but in discrete quanta. So, meaning that it the energy of the UV lights, for example, it has certain fixed amount of energy. Let's say, for example, let's say I put it in value. Let's say the UV light has energy at 200 joule, 500 joule, and then 1000 joule, for example. 200, 500, and 1000 only. That is some particular value only. We call it discrete quanta. So it is not continuous. Continuous is like the energy of the wave is like having all kind of value, from any value from 0 until 1000, for example. So if they can take all kind of values, we call it continuous. So it is not the continuous, it is the discrete case actually. So it takes fixed value of energy. So they are trying to say that. So just fixed value. Then photon is the particle in the electromagnetic radiation, for example. So like what I said, is a packet of energy. You put the energy in the balloon, then the balloon strike the electron come out. It's that kind of concept. So let's see the energy of a photon. Energy of a photon of an electromagnetic radiations of frequency f is given by this formula. So this is the formula to find out the energy in the UV light, for example. So you just take the Planck's constant, this value, multiply with the frequency, then you will get the energy of photon. Energy of photon. Let's use this formula. Okay. So frequency of the UV light, of course, they have to give you, then you can work it out. Then next one, we have the work functions, which is phi, work function. So which is the minimum amount of energy required by an electron to escape its surface. So logically, if the energy is not enough, the electron cannot release. It is still attracted by the nucleus of the atom. So it requires certain minimum amount of energy. More than that, then it will be enough to make the electrons overcome the attraction and come up from the atom. Okay, come up from the zinc metal, for example. So that is the work function. Work function is phi. If you have formula later, like phi naught here, which is the minimum amount of energy, phi naught. Yeah, it's minimum amount. Yeah, not and maximum. not a maximum. Oh, so for a given frequency, electrons are emitted with a range of kinetic energy. Because electrons deeper inside the metal lose energy in collision with atoms as they are emitted. Okay, so what they're trying to say here is, you imagine when a UV light with a given frequency, UV light with a given frequency shine on the metal, then the electrons get the energy, but some of the electrons are staying lower, not on the surface of the metal, so it's staying at the lower layer. So if they want to come out, right, they need to collide with the nucleus, maybe, they need to collide with other electrons in order to release from the metal surface. And because of that, the kinetic energy for those electrons is a bit lower compared to electrons staying on the surface. The kinetic energy will be higher. So that's why there is a range of kinetic energy. Okay, so there's a range. Okay, so we have two concepts already. Energy and work function. And then now let's see 12.5. Einstein photoelectric equation. Okay, so just now the E equal to HF. We can put it on the left. I can put it on the left. That represents the energy of photon, energy of the UV, for example, energy of the UV. This part is the energy of the electrons. Energy of the electrons is on the right. Energy of the UV light is on the left. So the energy of the UV light, some is used to provide the energy to escape its surface, which is called phi naught, which is the work function. So work function is basically the energy to make the electron release from the surface to overcome the attraction. And part of the energy from the UV light here is for the kinetic energy of the electrons. So left hand side is like input of energy, right hand side is how they use the energy. They use it to overcome the attraction, they use it to make the electron move. So there are two parts there. So that's why we have this equation here, which created by Albert Einstein. So where phi naught is the work function of the metal, so the value of phi naught depends on what metal we are talking about. Okay, so different metal will have different value for the phi naught. And then thus the energy of the absorbed photon is partly used to release the energy from the metal, which is phi naught, and partly to give it a kinetic energy, which is the E max. So the energy is used in two ways. So we can see that. Then after that, they modify the formula a little bit in this way. The phi naught, they change it to HF naught. HF naught, F naught is just now the threshold frequency, minimum frequency required to release the photoelectrons. So that is the F naught. So phi naught become HF naught. Then the E max become half mv square max. So we have this formula now. Okay, so we see electron deflections on the other side. So just now we mentioned wave particle duality, right? Is where the wave has have the particle behavior, have the wave behavior also. Okay, so which means the wave go through diffractions, go through interference. The wave has particle behavior, which is photoelectric effect. That is all about the wave. Now on this part onwards is the electrons. The electrons, the electrons that are moving, okay? Electrons that are moving have some wave behavior also, which is diffraction. Diffraction happens to electrons. Okay, so let's see what they talk about. De Broglie suggested since wave can behave like particles, particles should be able to behave like wave. Okay, so that is what he said, and then he do experiment to prove it. Okay, so the electron that is moving, right, this is called a matter wave. So it's a moving particles of metal of momentum p will have an associated wave of wavelength lambda. So imagine electron when it is moving. First, electron has mass. So if it has mass, then it has momentum. The momentum is mb, right? So electron has mass. So electron has momentum. And they also mentioned that the electron that is moving has wavelength also. Have wavelength lambda. So how to find the lambda? So you want to find the lambda, you just take the h, the Planck constant again, divide by the momentum, where momentum is mv, and then you take Planck constant divide by mass of the electrons, multiply with the velocity of the electrons, and then you get the wavelength. So where h is the Planck constant, m is the mass, v is the velocity of the electrons. So then you get the lambda, which is the wavelength, the de Broglie wavelength. Okay, so then how, when you have wavelength, right, so of course the electron should behave like wave. So we have to find out how diffraction happens on electrons. So what we do here is we put an electron gun here, then the electron come out, and then it moves straight, reach the thin graphite screen. Basically, thin graphite screen has small hole. Wave passing through small hole, then the wave band, and that is diffractions. So the electrons that passes through the small hole, they bend also. Okay, they bend. That is the diffractions that happens to electron. Some move in straight, some bend this way. So diffraction happens, and then when they reach the screen here, then you can see the effect. You can see the effect, where something like this is seen, showing that diffraction happens. Okay. Where the middle part will reach the end first, and this one will reach here later. So it's something like that. And the front view is like this. Okay. So the difference between these two is the voltage. If you use high voltage, then you can see the circle is smaller. If you are using lower voltage, the circle is bigger. Okay. They also say that when a beam of electrons strike thin carbon foil, a diffraction pattern is obtained on a screen, which is this one, the thin graphite is the thin carbon. When velocity of electrons in beam was increased by increasing voltage, you increase the voltage, then they will move very fast. So then after that, the rings in the patterns became narrower. So they don't diffract that much. Showing wavelength decreases as velocity is increased. Velocity increase, agreeing with de Broglie equation. So you see the equation, which is somewhere here. When the voltage increase, the velocity increase. So this one increase. This one increase, wavelength decrease. So it fulfills the equation fulfill the experiment. So that's what they say. Okay. So 12.8 energy levels. Okay, so first of all, this energy level is about the energy levels of electrons. Okay, it's about energy of electrons. So it is a little bit related to chemistry. You know, for example, if the electrons has less energy, then they will stay at the first shell. If it has more energy, then they will stay at the second shell, and so on. Okay, the higher the energy, then they will go to the higher shell. Okay, so now over here they said the energy of an atom is the total energy of its electrons. You imagine an atom has many electrons, and the electrons has many energies. So we total up the energy of the electrons, then you get the energy of an atom. So under normal conditions, an atom is in its ground state, where it possesses minimum possible energy. So for example, if you are not going through any chemical reactions or any you don't put any electricity on the atom, for example, atoms can you can use electricity to make it excited somehow. So if you are not doing all those things, right, you just put it there naturally, the electrons will have minimum energy, and we call that ground state. So ground state is also where we arrange the electrons as usual. Like first you fill up 2 electrons in the first shell, then second you fill up 8 electrons in the second shell, and so on. So we follow the basic rules to fill up the electrons. And after that, when the atom absorbs energy, so for example, electric shock or UV light shine on the atoms or the molecules, then they will have energy absorbed, and then they will come to excited state. So the energy of the atom increases, and the atom is in an excited state. Okay, so yeah, it's the formal term. Ground state and excited state is the formal term. Yeah. Okay, so we can use it in exam also. Ground state, excited state. Now, the excited state is unstable. It's unstable. So that means, imagine the electron who's supposed to stay in second shell, because you supply extra energy to the electron go to the fifth cell. So it stay at the fifth shell, and that is not stable. So eventually the electrons will come down back to the original shell that it's supposed to stay. So that's why you can see here, atoms eventually absorb energy, bringing the atoms back to ground state. Go back to ground state. So example, the situation will be like this. N equal to 1 will be the first energy level, or the first shell. Then N equal to 2, something like this. Then N equal to 3, and N equal to 4, and N equal to 5. So for example, so we have 1 electron here. So it absorbs energy, then it go to higher level. Let's say the energy that it absorbs is enough for the electron to reach the 4th shell. And then after that, it's not stable, then it release energy, and then it come back to the first shell, for example. So when this happens, so energy is released. So energy releases. For this case, when it go up, energy absorbed. So we have two situations here. Okay? Energy absorbed to go up, and then energy releases when it go down. Okay, now let's move on. Next page. So on this page, you can see electron release energy in the form of electromagnetic radiation. So if you still remember the diagram just now, so I draw an arrow which go up, and then after that, yeah. Uh-huh. Yes, the electrons stay in the shell. Yeah. So yes, it's the shell of the atom. And in A level, the shell is called energy level. Yeah. Okay. So what happened is it absorbs energy, it become excited state, and then it releases energy and it become ground state. So during the process of releasing energy, electromagnetic radiation is emitted. Maybe you feel like, oh, what kind of electromagnetic radiation? Is it gamma ray, or is it UV ray, or is it visible light or radio wave? So which electromagnetic radiation is emitted? So we need to do calculation to find it out. It depends on its frequency, of course. So that's why we have formula here. So which is on the next point. They said the frequency of the emitted radiation is given by HF equal to E2 minus E1. E2 minus E1, where F is the frequency of the electromagnetic radiation. E2 is the energy of the higher level, and E1 is the energy of the lower level. So example again, let's say I use back the example just now. 1, 2, 3, 4, 5. So n equal to 1, n equal to 2, n equal to 3, 4, and 5. So that the electrons stay at the first shell, let's say. So which electron stay at the first shell? Example is like hydrogen. Hydrogen atom. Hydrogen atoms, if you still remember your chemistry, hydrogen atom has only one electron. And let's say that electron, you put it in a machine where it receives electricity, and then it receives energy and go to higher energy level. Then after that, come down again after you turn off the electricity. So it comes down and releases energy. So this is your E1. You need to know the energy level, or need to know the amount of energy when they are at this level. So after that, you need to know also the amount of energy it has when it comes to this level. So that is E2. This is E2. So when you do E2 minus E1, so basically you are finding the energy difference. And in other words, energy difference is the amount of energy it releases. Okay? The amount of energy it releases will be E2 minus E1. And after that, H is the Planck constant. You have to put the value there. Then you can find out the values of F. Okay? You can find out the values of F. So we will have examples to try it out afterwards. Let's finish up the theory first. Okay, next point. The frequencies of electromagnetic radiation emitted by electrons when they come down to ground state were found to be discrete, showing electrons can only absorb certain discrete values, and hence we say the energy of an atom is quantized. So that means, for example, let's say I put value. At ground state it has, let's say, 100 joule. Now, in order to reach n equal to 4, right? So let's say the energy is 2000 joule. Okay, so from 1000 to 2000, right? That means to reach this level, they have to absorb 1900 joule to reach here. From 100 joule, absorb 1900 to reach this level, which is 2000 joule now. 2000 joule. So now when they come down, they have to release 1900 joule as well. So the energy that release is cannot be any value, you know, it is a particular value. You know? So if it releases 1900 joule, then we know that it's from n4 to n equal to 1. We know that because it has fixed value. Okay, then we call that quantized. Quantized. Okay? So which means they have discrete values. There cannot be any values that you may expect. You know? So cannot be continuous. Must be any fixed value. Okay. So yes. For example, let's say I take other value lah. Let's say I take other energy level. Let's say for example, this one is 1100 joule. This one, to come to this level, you need 2000 joule. Let's say this one you need 1800 joule. This one, let's say you need 1500 joule, for example. So meaning that you want to absorb energy, you either absorb 1004 to reach here, or you absorb 1700 to reach here, or you absorb 1900 to reach here, or you absorb 1000, let's say 210, 2100 joule. Okay? Or you absorb 2000 joule to reach n equal to 5. Okay? So it is fixed value, you know, it's fixed value. That's why we call it discrete. When you release also, you cannot simply decide, oh, I want to release 20 joule. Cannot one. You either release 100 joule to come here. Let's say like you are now at n equal to 5. You either release 100 joule to reach here, or you release 200 joule to reach here, or you release 600 joule to reach here. And again, it is just some particular value only. It cannot be any values that that we can think of, you know. Cannot be any value. Just only for some particular values. So that's why we call it discrete. So you get the idea now for discrete value here. Okay. Yes. For example, n equal to 5 to n equal to 4, you have to release 100 joule. Yes, you can't go lesser. You can't release 50 joule, for example, because you can't go to anywhere, you know. So you have to release 100 joule to come to n equal to 4. Or yeah, or you release 300 joule to come to 1800 joule. You know, yeah. So must be fixed value. So cannot be any values, fixed value. So that's why they write the important words here: discrete values and quantized. Okay, so quantized means discrete basically. Okay, now you see what we see when the idea here is quantized. So what we can see from our eyes will be something like this. Okay, this is the one, number 2 and number 3 lah. But I go through the first one also. So we are using a light bulb. The light bulb will release white color light. So this is white light. Okay, white light is released from the light bulb, and then you make the light passes through diffraction grating. Diffraction grating is a piece of material with many holes. Then the light pass through the small holes, and diffraction happens. That means the light wave will not travel in straight anymore. It will just bend. The wave will bend. So from something like this, something like this, then it bend. That's diffractions. And because of the diffractions, the white light, which is made of 7 components, the rainbow color, so it is separated. So it's separated. The red color light will stay here and then keep changing. Red, orange, yellow, green, blue, and then indigo, violet. So they will follow the rainbow color. Okay? So it forms a continuous spectrum. So that means all the rainbow color are side by side, stick together. So now let's see the discrete and quantized concept here. We have to use a different scenario. Okay, so 2 situations. The first situation is you use hot gas. So you let the hot gas passes through diffraction grating, and then you have the diffractions that happens, and then after that you can see lines at just some particular value only. Like for example, here you can see red, then here you can see yellow, here you can see green, blue, then maybe indigo and violet. Okay, so what happened here, I write down first. Okay, so you put a high potential difference. A high potential difference is put across low pressure gases. Okay, so try to imagine. So you have low pressure gases, then you make them taking the high potential difference. That means take some electricity, and then after that they will form lines on dark background. Okay, so this is one idea. It is similar to what I mentioned here, similar to this concept. So the hot gas, right, they are already in excited state. Okay, they are already in excited state. Maybe the gas molecules, some of their electrons are staying at higher level, n equal to 4. Then they release energy. Okay, so let's say from here to here they release, and then the energy release have certain frequency. That frequency represent green light, and then the light will be here. The light is shown there. Okay, so how come there are so many lines? Basically because there are different kind of way to release energy. Okay, different kinds of way. So for example, I just put it in general. Okay, so it's like let's say from n equal to 5 release to n equal to 2, then you get violet. Okay, so maybe I put a few more lines. Let's say I put until 7. Okay, say 6, 7. Okay, so let's say for example, from 7 release to 2, then they form violet. Then after that, violet. Okay, after that from 6 release to 2, they form indigo. Then after that, let's say 5 to 2, they form blue. And then after that, 5, 7, 6, 5. Okay, 4 to 2, let's say they form green. And then 3 to 2, let's say they form another color. Let's say yellow. Okay, so example will be like this. So that's why there are 7 colors there, 7 colors. 7 colors, strictly speaking, there is certain rules to follow. Okay, so the rules, of course, I know because this is in chemistry. They have to come back to level 2, then they will form some electromagnetic radiation where it is under the visible light. So if they come back to 2, then we can see it as visible light. Okay, so this is just example lah, no? Okay, so now let's see another situation. Any question or not for this one? Oh, okay. They are hot gas, right? Basically, because they are at the excited level. The electrons are in excited level. And then, they are not stable. So they will come down to lower level to go back to ground state. So to go back to ground state, they have to come down. When they come down to lower level, they have to release energy. So when they release energy, then they form the lines. The main idea is like that. Okay, it's just that when they release from different level to n equal to 2, they will form different color. So that's why you can see different color there, and you can see the idea of discrete values here. Okay, discrete value of quantized here. Yeah. Uh, it is black because it is not the white light that separate to rainbow color. It is the electron that come down and release a discrete value of energy, and which form one line here, let's say for example. Then if they release this different discrete value, and then they form another line, let's say. Something like that. The middle 2 line, this is the green. Basically, it's the rainbow color. It's the rainbow color. It's like red, orange, yellow, green. These are 2 lines, of course. There are certain reasons where we are not going to pay attention on that. Okay, we just need to know they come down, they release energy at fixed value, and then they form certain lines. Okay, so whereas the third one, right, is this particular line is missing, and so on. So we need to know why certain lines are missing there. Yeah, you can see here. This is the rainbow color, right? I see here, black color. Meaning that the red color light is missing here. Why this is missing and why this is missing? You see, this is the yellow, right? In the yellow region, and this line is missing. So that's why you see black here. Yeah, that represent missing. Okay, so what happens? Okay, let's see. I put it in blue color. Okay, so you see dark lines over there because absorption happens. So that's why this is called absorption spectrum. Absorption spectrum. Okay, so you see how we do it is in different way actually. Okay, so we pass through the white light through the cold gas. First of all, you have to know that the white light has white color. I mean the white light is white. I mean the white light has 7 components. Have 7 components which supposed to form this. So to form the continuous spectrum. But what happens is when you pass through the cold gas, so the cold gas is in ground state basically. Their electrons are in ground state. And then something happens there is they follow this situation. They will come up, they will absorb energy and go up. Okay, they will absorb energy. So they have to absorb energy from the white color light here. No? They absorb energy. So for example, to absorb from n equal to 2 to n equal to 3, let's say for example. Okay, so I put it in this way. Okay, I draw a few lines first. 1, 2, 3, 4, 5, 6, 7, and so on. Okay, this is n equal to 1, 2, 3, 4, 5, 6, 7, and so on. Okay, let's say if you want to, if the electrons stay at this energy level, if they absorb energy and come here, then they absorb away the red light from the continuous spectrum. So that's why this line is missing, because the energy is used to absorb light. So that they come from n equal to 2 to n equal to 3. And they absorb light. Then after that, let's say for the next one, this one, to absorb this yellow color light, so they have to start from n equal to 2, absorb this fixed amount of energy, and come to and form and absorb away the yellow light. So yellow light. Then after that, here to here, green light. Okay, let's say here to here, let's say blue. Okay, let's say here to here, purple or indigo. Okay, let's say indigo. And then one more level, purple. So, okay, something like that. Okay, they have to absorb energy, and because of that, the continuous spectrum has certain line which are not there. Okay, so it's absorption. This one is absorption concept. Okay, so now let's see the words given there. This one is from ground state to excited state. Yeah, I write down. Ground state is the cold gas. Cold gas is in ground state, and then they are going to excited state. So to go to excited state, they have to go up, so they have to absorb energy. Absorb energy. The source of energy is from the white color light, and compared to this one, this concept, this concept is for this. Compared to this one is the hot gas is in excited state. It's in excited state. So what happened is they have to release energy. Release energy and go back to ground state. When they release energy, then they form the lines. So this concept is for the hot gas. So two different concepts here. So this one is for this. All this. Going down and form certain lines. And this one is for this. Go up. Go up and absorb energy. Okay, so you can see so many things happen in one small little atoms or molecules. So something like that can happen. Okay, we see the theory over here. First, they say emission line spectra, which is this one. Emission spectrum. Spectra is basically the plural. And this is the singular. This is plural. The composition of light emitted by a hot gas. So you have to know that hot gas is currently in excited state. Then what happened is not stable, release energy and come back to ground state. Okay, so let's see here. So what they say now is they said the frequencies emitted by atoms of a substance when they de-excite from higher to lower energy level. So they are trying to say that this is emission line spectrum, right? It is for this case actually. For this case, so this case, so they will come down. So that's why they call it de-excite, from excited state back to ground state. So that is de-excite, and then they release energy. They release energy. So they release energy, then they form certain lines. Okay. Then next one, absorptions line spectra. When white light is passed through a cold gas. So you can see here, white light, this is the white color light, passed through the cold gas, and then the cold gas absorb energy. Then certain lines are not there. Okay, you can see here, the frequency absorbs from a continuous spectrum by the electrons of a substance. So which means the electron absorbs certain frequencies, and that's why certain frequencies is missing there. Then the emission and absorption spectra are characteristics of each element. So they are trying to say that different elements, the absorption spectrum and the emission spectrum is different one. Yeah, it's different. So this is just for one particular kind of gas, okay, where it looks like that. Okay, so of course different element at the end will be different gas. Okay, so this is about band energies in solids. So band energies. It's a new idea. Okay, let's see what is that about. Atoms in solid are close together, and electrons from one atom interact with those of neighboring atoms and altering energy level diagrams. So that means they are giving us a few information here. First, we know solid, they arrange, the atoms arrange themselves in this way. So very close together, something like this. So at the meantime, the electrons interact with one another, not just within the same atom, but with the neighboring atoms as well. So by right, the energy level diagram supposed to be like this, where n equal to 1, n equal to 2. So this is the energy level diagrams or the shells of the atoms. So where first shell has lowest energy, second shell has higher energy, and so on. Supposed to be like that one. But because of the interactions, the energy level diagram is no more in this way already, but it is in this way because of the interaction. Okay, so how are we going to understand this? First, you can see here that is electrons energy. Okay, so we have many energy levels here until we call them a band. We call them an energy band here. So after that, here there are many energy levels as well. When there are one atom, it's supposed to be like this only, but because of the interaction, then they have bands here, and then there is a gap with no energy here, and then there are bands over there. So this is the second band. You can see that many energy levels interact and very close to each other. Then after that, this is also a band. Okay, so we have a particular gap here, which is called forbidden gaps. It is where this place has no energy level. So you can see 3 energy bands altogether and 2 forbidden gaps. Okay, so this happens in solid. Just for your information, this happens in solid. In gas, they are not close to each other, and in that case, the energy level diagram will be like this. So this kind of energy level diagram is for gas. Okay, it's for gas, and then this kind of energy level diagram is for solid. Okay, of course, this is the more complicated version. In past paper, they give us a simplified version. So they give us something like this. I just let you see first. In past year, they put only 3 bands. Only 3 bands. So this is more than 3 bands because this is 1 band. This is also considered forbidden band. Okay, forbidden band. You can call it forbidden gaps, but at the meantime, it also represents a band with no energy level. So this one is 1, 2, 3, 4, 5. 5 bands. But in past year, they will only test you on 3 bands. So which is like this. They give us 1 band here. So this band, okay, yeah, I repeat again for the 5 band. So this is the first band. This is the first band. So number 1, first band. So this band is normally known as conduction band. So how it works, of course, we will see that later. Then this is the second band. This is the third band. This is the fourth band. This is the fifth band. So altogether there are 5 bands. But in past year question, only 3 bands will be tested over here. So which is like this. which is like this. So the first band that I put in rectangle here, that means they are something like this. They are something like this. Okay, something like this, many energy levels, and then they form this band. So this band is named as conduction band. Okay, so conduction band. So what is conduction band? Imagine metals. Metals can conduct electricity. So when it can conduct electricity, that means the electrons are free to move around and carry the charge. The charge is moving, So they need to go to the conduction band in order to move freely. So if they are not in conduction band, they are attracted by the nucleus, so they are not moving freely. So conduction band is related to the electricity conductivity. So after that, we have the forbidden band. So forbidden band is the one, the region with no energy level, and then we have the valence. Yes, in my notes I use forbidden gap, but forbidden gap and forbidden band is the same thing. Yeah, it's the same thing. So meaning that in past year they combine it. They combine this whole band and they call it valence band. They call it valence band. Valence band, forbidden band, and then this is conduction band. So only 3 bands. Okay, so the other thing is, it's not enough. This is just general, and solid itself is subdivided into three types of solids. So we need to know how their bands look like. So the first one is metal. Okay, so metal, we have their band look like this. So I write short form. Conduction band, I call it C. Valence band, I call it V. Forbidden band, I call it F. Okay, so metal, the conduction band is here, the valence band is here and here, and then the forbidden band is in between. Now let's see the second one, semiconductor. So first of all, we have to know semiconductor, their conductivity is poor compared to metal. So it looks like this. Valence, forbidden band, and conduction band. Okay, so semiconductor, we need to know one thing for temporarily. After that, there we have more information coming in. So you want to make semiconductor conduct electricity. So basically, you need to make the electrons shift from valence band to conduction band. So the electrons have to take some energy to jump across the forbidden band and come to conduction band. That means they need energy to go to higher energy level. And once they reach here, then they can conduct electricity. Yes, no electron there. When it is under normal situation, no electron there. So they need to absorb energy to go there and then can conduct electricity. Okay, then finally we have the insulator. Yeah. The valence band is overlap with the conduction band for metal. So where the electrons that at this particular valence band, they are at the same time able to conduct electricity. So they are not going to take energy and shift to conduction band. This one is readily, it's ready to conduct electricity at original state. Yes, no need to transfer. So the electron here is ready to service. It's something like that. Okay. Then, okay, insulator. So insulator, basically we have a conduction band with no electrons, and then there is a very big gap for the F, and then the valence band is very far below of it. The problem is, first, no electron in the conduction band, so that's why I cannot conduct electricity. So the forbidden band is very large, and then the valence band has electrons, but the electrons could hardly reach here. Not enough energy to jump across to this level. Not enough energy. Okay, so because of that, insulator cannot conduct electricity because no electron can reach here and move around freely. So that is the characteristics. Okay, so now one more things to pay attention. Beside the diagram, we also need to pay attention on how to put everything in words. Okay, so of course, I just write down some of the important points. Of course, this is from the mark scheme itself, which is relevant to this. Okay, so first, this is from mark scheme on how to explain this kind of thing in exam. Okay, so the first point we can say, in a solid, electron in neighboring atoms are close together and interact. So it seems like this is same with the note. Interact with each other. Okay, this is the first point. It is a 3 marks question actually. 3 marks. So second thing, these changes their electrons energy levels. This one second point. So that's why the energy level is not like the one that we discussed before. It is like this. Okay, then after that, this, okay, sorry, many atoms in lattice cause a spread of energy levels into a band. So that is how the thing works, or how the things come from. Okay, now let's see the next point here. And electrons can have an energy at any level in one of the energy bands. So electron can have energy here, can take more energy and come to here, or can take even more energy and come to conduction band. So however, it cannot have energy which lies in the forbidden gap. So there are no energy level in the forbidden gap. So they either stay at this, or they take more energy until it's enough to reach here, or they can even take more energy so that it is enough to reach here. So if they have energy in between and the electron come to the forbidden gap. So basically, they cannot stay here. They need to release their energy and come down. Okay, so let's move on. Next bit. Yeah. Yeah. Let's say, for example, the electron can stay here in the valence band, and then they can maybe they have absorbed energy. Let's say you heat up the atoms, you heat up the solid, then they have absorbed energy. Then maybe you don't heat it up too much, you heat it up a little bit, then the electron can come here. And forbidden gap is where electron cannot stay with no shell over there. So if not enough energy, then they have to release their energy and come down. Yeah. So if they have enough energy to reach here, then they can stay here. Then they can conduct electricity then. Yeah. So the idea is like that. And let's move on. Okay. Now, band theory and electrical conductivity. So first, in a metal, the conduction band is only partially filled with free electrons, which gives the metal its conductivity. Okay, so as you can see, something like this. Okay, so where this is the conduction band with electrons. This part, no electrons. So that's why they say partially filled. So partially filled. Okay. Then in an insulator, or maybe I give you one more information first for metal. At this point, they say I have information here saying that free electrons in conduction band have broken and then free from individual atom and are able to move through the material. So that means they can conduct electricity. Okay. Yeah. So they can move everywhere and conduct electricity. Okay. Now let's see insulator. In an insulator, the conduction band is unoccupied. Just now this is partially filled. This one is unoccupied. And the valence band is fully occupied. So valence band full of electrons. But conduction band, no electrons. So that's why it cannot conduct electricity. So the electron who can come to conduction band, basically they are free electron. So no electron there, so cannot. Now in a metal, the conduction band overlaps with the valence band. So this is the overlapping region, allowing it to conduct electricity. When a metal is heated, resistance increases because there is no increase in density of electrons in the conducting band. Instead, atoms vibrate more and electrons collide more frequently. So what are they trying to say is, you imagine when you heat up the metal, so what happens inside the atom is like earthquake, so they are like vibrating more. So something like earthquake happen. So the atoms is vibrating, and at the meantime, collide between atoms, electrons happens more frequently, and because of that, the conductivity of metals decreases. Conductivity of metal decreases. Why is it like that? It is because the electrons want to flow to conduct electricity. So the electrons is like a car, for example. So when earthquake happens, the car could hardly move on the road. So maybe the road is shaking, or maybe there's something blocking or vibrating. So it is that kind of scenario. Try to imagine that. Okay, so what we can say here is when the temperature increase, conductivity of metal decreases. Okay. The explanation, right, of this thing, you can just follow the past year question where we are going to do afterwards. And this is 5 marks question. So the explanation of this alone give you 5 marks, a lot actually. You just need to memorize and just warm it up everything. So it is a chance to score 5 marks. They give you many lines with for you to write. Okay, so we will go through that later. It is more or less like this, but the thing is, instead of memorize this, we better memorize the mark scheme. So we will come to that later. Okay, now let's see the next point. In an insulator, there is a large forbidden gap. So this is where we discussed just now. This one is large enough until the electron could hardly reach there. Okay, there is a large forbidden gap between the valence and conduction band, and voltage is insufficient to lift electrons across the forbidden gap. Okay, so cannot reach there. And then, so hence no electrons in the conduction band all the time, and then cannot conduct electricity. Now we have this in an intrinsic semiconductor. So this one I explained a bit first. We have 2 types of semiconductor. One is intrinsic and the other one is extrinsic. So intrinsic means pure semiconductor, pure. Extrinsic means they are not pure. You add some other atom inside into the semiconductor. Okay, so semiconductor in chemistry, right? If you remember your periodic table, they are like group 14. Some of the members are from group 14, like silicon. Okay, so let's see. In an intrinsic semiconductor, that means it's pure, it's just 100% silicon. So its conduction band is also empty. So it's also empty under normal condition. For example, room condition, it is empty. However, the gap between the two is very small. So you can see narrow gap here. When heated, electrons gain energy to jump into the conduction band, and the material will conduct better. So heat, then jump here, and conduct electricity. So this is different from metal. When the temperature increase, conductivity of semiconductor increase. So this is different. Okay, so you see metal, right? Metal, when temperature increase, conductivity decreases. Of course, the explanation is because the atoms is vibrating and blocking the flowing of the electrons. And maybe you're wondering, how come this is not blocking? Okay, because the electron jump over to the conduction band where there is no atoms here. No atoms here, so then they can move freely. Not like this one, they are like overlapping. So the atoms and the electrons are staying at the same region, and then when it's heated up, then they vibrate, and then they block the flow of electrons. Okay, so it's different in this way. And then let's see. Okay, this one we have done. Okay, here, in and LDR. Yep. Yeah, extrinsic. Okay, I write down. Extrinsic semiconductor. Yeah, it's not pure. This is extrinsic semiconductor, not pure, and their conductivity is better actually. They have add some other atoms inside to make the conductivity better. So like silicon add with something else, add with other elements. Yeah, but it is not under our discussion here lah. Okay. So okay, now let's move on. Okay, maybe I can give you also how we get 5 marks at the meantime. Okay, how they get 5 marks. So let's discuss this also. Okay, so let's see this one. How to get 5 marks. So the first mark, you can say in metal, conduction band overlaps valence band. Number 2, you can say as temperature increase, no increase in number of free electrons. Number 3, as temperature increase, lattice vibration increases. And number 4, lattice vibration is the atoms is vibrating. Then lattice vibration restrict movement of electrons. And the 5th point, current decrease, because electrons affect the current. Current is charge over time, right? So current decrease, and so resistance increase. Okay, so this is how they get 5 marks. Okay, now let's see in semiconductor, the example here, LDR, light dependent resistor. So in an LDR, so LDR, make sure you remember the basic concept. Basic concept of LDR. Yes, LDR is light dependent resistor. Oh, what meaning is that? Oh, yeah. So, are you planning to have LDR? No. Okay. So, and many people have that long distance relationship. Okay, so yeah, I recall back my university life. Some people have LDR, and after that, broken already at the end. Okay, so this is the basic concept of LDR. Resistance decreases with light. Resistance decreases with light. Okay, so basically, if you understand the idea here, I think it should be easier for us now. The LDR, which is a semiconductor, they absorb light, then the electron jump to the conduction band, and then electrons can flow, and hence the resistance drops. So yeah, LDR itself is accepted. No need to write full terms like dependent resistor. Yeah, it's accepted. Uh, light dependent resistor, LDR. Yeah. Okay. So let's see how it works. Photons of lights. Photons again. Photons mean the packets of energies. So imagine the light has energy, the energy that put inside a plastic bag, something like that. So it seems like it become a particles already because you put the energy in the plastic bag. It seems like it's a particles. Okay, so photons of light are absorbed by electrons in valence band, so they jump the gap into the conduction band. So this explanation is too short, because in exam, again, they give 5 marks. You imagine they ask this 5 marks, then they ask this afterwards, another 5 marks. So the question can be 10 marks questions. Okay, so it's possible. So if they ask 10 marks and you remember the fact, and then you can score already. Okay, let's see how. This one they asked in 2016 June 43. Question 12b. Okay, so how to answer about LDR is first, we said photons of light give energy to electrons in valence band. Okay, this point same with the note. Then second point, electrons move into conduction band. Then after that, leaving holes. You see, our notes never mention hole. Leaving holes in the valence band. Yeah. So holes is actually what? Imagine the electrons is initially stay at a particular place. So when the electron go away, so you imagine, you look at this picture here. Okay, so which is here. Oops. Okay, so this is the one. Initially, electrons stay here. Then after that, they get energy and jump to conduction band. So leaving this place, which is originally occupied with electron, now they leave already. So this become the hole. So hole is positively charged. Okay, you have to know that holes is positively charged. Initially, when electrons are here, right, so they are neutral. So when the electron move away, then it become positively charged. So we call this holes. So basically, holes is a place where it attracts electrons. It attracts electron, to fill in the gap. So electron can come, can move, and come and fill up the holes. Okay, so that's why electrons and holes are both known as charge carriers. So this carry negative charge, this one attract the electrons. Okay, so let's continue. Leaving holes in the valence band, and then next point we can say these electrons and holes are charge carriers. When current, at the end current increase and resistance decreases. So let's look at this question. State an effect, one in each case, that provides evidence for the wave nature of a particle. Okay, so imagine that we learned this in the notes before, where electrons can go through diffractions. So electron is the particle, diffraction is the wave nature. So we can say that this is electron diffractions. So electron diffractions. Part 2, the particulate nature of electromagnetic radiation. So for this part 2, the electromagnetic radiations, for example, is the UV light that shine on the metal, and then the metals, the electrons on the metals get energy, and then the electrons come out. So the particulate nature is like collision happens, like the UV lights having collision with the metal and then make electron come out. So this is called photoelectric effect. Now we look at B. For electrons, energy levels in an isolated atoms are shown in figure 12.1. For the emission spectrums associated with this energy level, on figure 12.1, mark with an arrow the transition that gives rise to the shortest wavelength. Okay, so to understand this shortest wavelength, we start from V equal to F lambda. So in order to get shortest wavelength, so the frequency should be the greatest. Just for your information also, V is constant. V is constant, which is, the electromagnetic wave. The V is 3.0 times 10 to the power of 8. Okay, now if you want to have maximum frequency, then based on the formula, delta E equal to HF. So the F is maximum, the change of energy should be maximum as well. So when you mark, you have to mark from the highest energy level to the lowest energy level, so that there is a greatest change of energy, and hence the frequency is the greatest and the wavelength is the shortest. Now we look at part 2. Show that the wavelength of the transition in part 1 is 4.35 times 10 to the power of negative 7. So for this part, to show the wavelength to be that value, now we have to use the formula delta E equal to HF. but we don't know the frequency. We know the h. H is basically the Planck constant, so we know that, and we don't know the frequency here. So we make use of v equal to f lambda. We rearrange it to get f equal to v over lambda. Then we substitute this to the formula here. So delta E equal to hv over lambda. So delta E is the change in energy. So we rearrange it in this way first. We put lambda as the subject, hv over delta E. Okay, so now we substitute with value. So the h is Planck constant, 6.63 times 10 to the power of negative 34. The v is the speeds of the electromagnetic wave. Okay, 3.0 times 10 to the power of a. The delta E, you have to be careful. Our delta E must be in SI unit, which is in joule. So you need to know they are giving us electron volt. So 1 electron volt is basically 1.6 times 10 to the power of negative 19 joule. So to find the change in energy, so we need to take the higher energy minus with the lowest energy. So which means we take negative 0.54 minus with negative 3.40. So we get the answer in terms of electron volt. So we time with 1.6 times 10 to the power of negative 19. Then we can change everything back to joule. Okay, and then by pressing calculator, you will get 4.35 times 10 to the power of negative 7 meter. Okay, now let's look at the other side of the questions, which is here. State what is meant by de Broglie wavelength. Okay, so this is a wavelength associated with a particle that has momentum. Okay, now part 2, calculate the speed of an electron having a de Broglie wavelength equal to the wavelength in B part 2. Okay, so to count the speed of an electron, so we have to use the de Broglie wavelength formula, which is lambda equal to h over mv, and then we substitute with value. The lambda, we found it in the previous part, which is 4.35 times 10 to the power of negative 7, and then the h is the Planck constant, 6.63 times 10 to the power of negative 34. The mass here is the mass of the electrons. So the mass of electron is 9.11 times 10 to the power of negative 31 times v, and then we have v equal to 1.67 times 10 to the power of 3 meter per second. So that is the answer. So we fill it up here. 10 to the power of 3 meter per second. Okay, so this is all about our question here.